In the last video, we looked at what a vector was. Now we're going to take a look at what a matrix is, and in future videos, we'll look at how we can interact both vectors with other vectors and matrices with other matrices, as well as vectors and matrices together. So in the last video, we defined vectors in a very specific format. We said that we can have a vector in 3D space. You can have an x component, a y component, and a z component. And we used velocity and force to define a physical representation of our vector. We also talked about using the basis vectors I hat, j hat, k hat to define it in a different format, right? So we were able to say that we have a direction because there's an x component, y component, z component, and so there's a specific direction. This vector with an arrowhead is pointing, and it has a magnitude, a length scale, right, which we define by this variable form. Now, this is a very specific kind of vector, and it is used a lot, but there is a more general type of vector. The more general type of vector is just looking at a series of numbers. So I can define a vector with more than 3 numbers in it. I can have a list of numbers in there. And it may or may not have a direct physical representation. This could be something that I use to help solve a mathematical equation that's between solving properties. This is done very often. You can even generalize it to a larger scale. I have a group of students in my class, and I am making a list of how much money they have in their wallet. So has a physical representation, but it's not an XYZ representation. It's literally just a list. And we can write this list in a row, right? Or in a column. It doesn't matter. In either way, we can identify different terms with the indice. So let's say I call my vector v. If I call for the first value in my vector v, I would grab the far left number, 5. If I call for the second one, I will grab 9. If I grab for the third one, I grab number 2. Also works in the same way if it's a vertical column. When we switch something from a horizontal configuration to a vertical configuration, this is known as transposing. And it's fairly straightforward when we're looking at just a vector, but we're going to take it one step further and now look at a matrix. When we look at a matrix, we take a number of vectors and we stack them, either a number of rows and stack those rows, or a number of columns and stack those columns. Depending on what your matrix represents, the order may or may not have a real meaning, but it is important that you understand what the order you place them in so that you know how to use them effectively, right? So sometimes we have square matrices. All a square matrix means is the number of cells you have in rows, number of columns you have is the same as the number of rows. So here we have a 2 by 2 square matrix. Here we have a 3 by 3 square matrix. That's all it's represented. There's a couple ways we can define a matrix. Remember, when we define a vector, we use bold and put an arrow above it. Typically, vectors are described with a lowercase value, and matrices are described with a capital letter. Now, it's not a hard rule. You can define them in either case, but that's a common practice. You can draw square brackets around a matrix. This is not often done because it's a little tedious, but when you first define it, that might be a way to use it. But afterwards, usually it's just a capital letter. If you can bold it, usually it's bolded. And you can call for values within the matrix, similar fashion that you can call for a vector indices or cell values, right? So index 2 refers to that cell. Now, with a matrix, you have 2 dimensions, right? You have rows and you have columns. So the first value tells you which row you're looking at, and the second one tells you which column you're looking at. So if I'm looking at the matrix A, the first row is the top row, and the first column is the far left column. So 1 is this top row, 2 is the second column. So this will be the value 3 for matrix A. For matrix B, I'm looking at 2, 2. Whenever the value for a matrix, whenever the index you choose for the row and column are the same, that means you're looking across this diagonal, because this is the 1, 1, this is the 2, 2, this is a 3, 3. So row 2 is right here, column 2 is right here. So that'll be cell number 5. Okay, now you don't have to have a square matrix. You can have a non-square matrix where you have, like here, 2 columns and 3 rows. Or like in this case here, you have 3 columns and 2 rows. It really depends on what you are building your matrix out of and what you want to use your matrix for, right? So maybe the columns represent a time component, and the rows represent a specific person or a specific object you're measuring. It could mean anything, right? So you describe it. It's up to you how you describe it. In the more general form, we can write it with subscript indices. So the little a represents the cell value. The subscripts represent the row and column. So this matrix here is non-square unless m is equal to n, right? So we go from A11 all the way to A1n. So A11, A12, A13, also that's what these dot 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 represents. And then we go down the number of rows from A11 all the way to AM1. So there's m rows and n columns. So this one's going to be AMN. Now across the diagonal, they're not going to be the same as if it was in a square. In a square matrix, these would be all AII, right? A11, A22, A33, and then if the number of rows and columns extended, it would just keep going in that fashion until ANN, right? So we have vectors, we have matrices. There's a more general form that you might hear of, and those are known as tensors. A lot of times, and I'm guilty of this too, a lot of times we call matrices tensors. We use them interchangeably. They're fairly similar. They're used for the same things. A matrix is just a more specific form of a tensor. A tensor is any list of numbers with a variety of ranks or dimensions. So I think I've used the term dimension already, right? When we look at a vector, we're looking at one dimension. It is going in, you can think of it as 1D, right? If you're going across a line almost. And a matrix is like a plane, right? This is a plane, this is a surface. So this is considered 2 dimensions. You can also call this by rank, a rank of 1, a rank of 2, and so forth. A tensor is something more general. You can have more or less, and you still can call it tensor. Tensors are often also used to manipulate things, but I've heard the term used for matrices. So I'm not so specific. So I'll use the term matrix in the most general form, but know that like mathematicians are more specific and they want to use tensors and matrices in a separate way. So in a graphical sense, we can think of a scalar as a tensor with rank of 0. This is a single number, okay? Then when we go to a vector and we say its rank of 1 or dimension of 1, then we get one scalar and we put it in a list, either in a row or in a column like we see here, right? That's when we call it dimension 1, has a dimension of 1 or rank of 1. And then a matrix we already saw, we get a vector and then we build upon that, right? You get a vector in the column and you build upon that, or a vector in a row and then you build upon that, right? Depends how you look at it. So if you have something higher than rank 2, we often use something in rank 3. You take a matrix and you stack on top of it. So an example of this that I work with my students in class is if you're looking at a plane, right, a surface, and you're measuring either the temperature or the stress on the. So every single point is going to have a property. It's going to have a stress, or it's going to have a temperature. It's going to have a pressure if you're looking at like a tank. And each of those will be represented in a matrix, right? So at a given time, I will have, let's say this is my surface, a temperature at this point, at this point, at this point, if these represent different locations, right? And then let's say this surface is being heated. At another time, you would have a completely different matrix that represents the temperatures at that time, and so forth as you move along time. Well, I can have this axis be my time axis, where this front surface is my first temperature distribution, and then as time increases, I have the second matrix right behind it represent the temperature distribution at that given time, and so forth. Now, the tensor could be even higher in rank. It could be 4 or 5. And all that means is you're representing different things across these different dimensions. Now, it's hard to physically visualize what that is, or what that represents, but one way to think about it is this. So in this matrix, we have a rank of 2. And so we have 2 indices, right? A, M, comma, N. We have, when we call a cell in here, we say A1, comma 2. Now, if we have a tensor with rank 3, we would have 3 indices. It would be A, M, N, O, or, a third letter. If it's rank 4, then you would have A, M, N, O, P, let's say. And then when you call a cell in there, it'll be A, I, comma, J, comma, K, comma, L, or whatever you want to use as your dummy variables. All I'm trying to say is, even if we can't physically look at it in the way that we have looked at these types of tensors, they physically do make sense, because all it is will be just adding commas to add additional indices. So those can be very useful if you're trying to describe a very complex system with a lot of different properties that you're varying. Now, the most common ones that you start with are your ranks 0, 1, and 2. You may start working with rank 3 tensors once you go into something with a time component. But what we are going to focus on are these 3. How does a scalar interact with a vector? How does a scalar interact with a matrix? How does a vector interact with itself? And how does a matrix interact with itself? And then finally, how does a matrix and vector interact with each other? There's a lot of different ways they can interact to solve complex systems. And we're going to start taking a look at some of the more basic ones in the next set of videos.